Okay, hello everybody. Welcome back to the Intercontinental Seminar Series of Gravity and Cosmology. Before we start the talk, on behalf of the organizers, I would like to wish you everybody a lovely, wonderful, and fruitful new year in 2026. So the first speaker of this year is Professor Pei-Ming Ho from National Taiwan University. And so let me briefly introduce Professor Ho. So Professor Ho, he received his PhD from UC Berkeley in 1996, and in 1998 he came back to Taiwan, and now he is a professor in National Taiwan University. So Professor Ho, he is an expert in quantum gravity, string theory, and also quantum aspects of black holes. So today he's going to talk about Hawking radiation and space-time uncertainty. So yeah, the stage is yours.
Okay, thank you. So I'm happy to have this opportunity to talk about my recent research. Thank you for your invitation. Um, so, let me start by reviewing the standard conventional model of black hole formation and evaporation according to Hawking and his followers. We consider in the past a large ball of matter collapsing under gravitational force. And at some point, the horizon appears. And according to Hawking, uh, observers at distance would observe particles as Hawking radiation. And this Hawking radiation, by definition, I mean, according to Hawking's calculation, is mostly only carrying geometric information. On the other hand, the collapsing matter carries other information, collapsing into the black hole, and eventually the black hole radiates and disappears or becomes a tiny black hole. So the question is, where is the information in the matter after this evaporation? Does it go into radiation or not? Is it like burning a piece of coal? When you're burning a piece of coal, you have a high temperature at the coal, and then the high temperature breaks bonds between atoms and molecules, and information inside the matter goes away, and there's some information that cannot be released at this burning temperature would remain in the ashes. On the other hand, Hawking radiation doesn't seem to be like that. So the question is, information in the matter, is it still preserved or not? In this talk, I'm going to use the natural units. So the Newton constant in four dimension is giving you this Planck length squared, and h bar and c are equal to 1. And also, I'm going to focus on spherically symmetric black holes, Schwarzschild black holes, and the Schwarzschild radius will be denoted by little a, and it's 2 times Newton constant times the mass of the black hole. So please feel free to ask questions at any time. And so the problem is that when the black hole radiates, according to general relativity, the horizon should be uneventful in the sense that if you are freely falling, if you are collapsing with the matter, you are actually, as you are under gravitational force, you are actually in the inertial frame. And when you're freely falling, you should feel like floating in space. So you would not feel like you are entering the horizon or anything in particular. So the equivalence principle tells us that we could be just crossing the horizon right now, and we would not know that as long as we are in free fall. So if the matter is falling through the horizon, it can no longer have access to the outside causally. All the information seems to be kept inside the horizon. On the other hand, when the radiation takes away all the energy of the black hole disappears. So there is an information paradox. So let me start with explaining the nature of Hawking radiation by reviewing Hawking's calculation. Here on the right, I'm showing a small portion of the diagram in this picture. So I'm showing this part. So I have the horizon at Schwarzschild radius, and then there is a collapsing matter. And people at distance detect Hawking particles at different time. If you trace the Hawking particles backward in time uh, to the point inside the collapsing matter, which is a Minkowski vacuum, because of the geometry of space-time, the shape of the wave packet is going to look quite different. And the reason is that there is a horizon, which means that when you receive a particle at distance, at a very late time, that particle is only going to be traced back to some point outside the horizon. There's never a particle outside that can be traced back to a point inside the horizon. So if you look at the correspondence between the time for distant observer, little u, and the time for Minkowski observer inside the collapsing shell, capital U, you see that when little u goes to infinity, if you trace it backward in time to observer inside the collapsing shell, it only corresponds to a finite value of u. So we can take this finite value to be 0, and then one can show that the relation between the two time coordinates is such an exponential relation. And therefore, correspondingly, there's a large blue shift so that a small momentum at large distance for a distant observer, p little u, is blue shifted to a very large momentum. The later time particles corresponds to a larger value of small u. It corresponds to a larger, further blue shifted momentum for observer inside the collapsing shell. And therefore, as you can see, the picture shows that the wave packet is distorted. The part at a later time is further distorted to a high frequency. And this difference in time for distant and near horizon observers tells us that the vacuum defined for the Minkowski vacuum defined inside the collapsing shell is perceived by distant observer as an excited state, because for the Minkowski vacuum, they define the vacuum by separating positive and negative frequency modes. But this exponential relation, this huge blue shift, gives you a different definition for distant observers about vacuum. And therefore, Hawking radiation is nothing but the reading of the Minkowski vacuum by distant observers. And therefore, by definition, it carries no information. It may carry a little bit of information about geometry if the collapsing shell is not perfectly spherically symmetric. Maybe some information can be delivered, but it only depends on the geometry. If there is some information hidden in the matter without changing the geometry, that information, according to Hawking's calculation, has no way of showing up in Hawking radiation. Furthermore, if you want to say that information actually comes out, actually it's you are looking at a scenario that's quite dramatic. So if you look at this picture again, we have a large ball of mass in the long past, and it undergoes collapse, gravitational collapse, and there is Hawking radiation, Hawking particle coming out. So let's say that the initial mass of this ball of matter is capital M, and we can ask how much time it takes for the mass to radiate 99% of the mass. So the remaining mass is m over 100. For a distant observer, the time it takes is very long. It's the page time. Schwarzschild radius to the cube over Planck time to the second. However, for a freely falling observer, this time is extremely short. It's only about 1,000 Planck time. So when you throw a piece of paper into the black hole, all the words on the piece of paper, and not only that, but also the atoms, the wave functions of the quarks inside the nucleus on the paper, they should all be delivered to a distance through Hawking radiation if you believe that all the information of collapsing matter should deliver to Hawking radiation. So that's a quite dramatic situation. So that's why in the firewall paper, they say either you have firewall or you would need non-locality in order to deliver information. If you believe information can only come out causally, then you have to deliver 99% of an arbitrarily large black hole within 1,000 Planck time. Otherwise, you have to say there is no local interaction that can give you information about matter inside the horizon. So you have to take either situation. None of each is a pleasant choice. So we have the black hole information paradox. Hawking's calculation is a calculation in low energy effective theory. And according to the calculation, Hawking radiation carries almost no information and it persists until almost complete evaporation. And so, as we mentioned above, there is a paradox. How is information preserved? And the big question is Hawking's low energy effective theory calculation reliable? So actually, in the early days, not long after Hawking's paper, a lot of people believed that his calculation was not reliable. But over the years, people checked his calculation carefully, and after a lot of works, people start to believe that his calculation is somehow reliable. So then people try to explain why. So one important explanation is called the nice slice argument. So the story is like this. You have this collapsing ball of mass, and then, but then you look at the trajectory of the Hawking particle. And so for the evolution of the Hawking particle, it only cares about the small region of space-time that it passes through. And then people find that you can choose time slices like these dashed lines. You can choose time time hypersurfaces as time slices such that every time slice is very smooth. The extrinsic curvature is small everywhere, even though it looks a little bit dramatic here. But actually, if you check, the curvature is very small. So then, according to the adiabatic theorem, when you have surfaces of curvature less than 1 over A, only excitations of energy less than of order 1 over A can be excited through this time evolution, unless you input some energy. So if you are not inputting any energy, then you don't expect high energy events to arise through time evolution. And therefore, if you start with a low energy, nearly vacuum initial state, then you expect a near vacuum state at late time. And as there is no high energy events, low energy effective theory should be valid. According to the decoupling theorem, UV physics is irrelevant. So they say the nice slice argument, since you have these nice slices available, you don't expect UV physics to be relevant. However, this argument has a loophole. Even though you have low energy states along the time slices, actually, if you try to do a experiment at transplanckian energies, you still need high energy physics. You still need UV physics to tell you what's the outcome of your experiment. And when you look at the Hawking particle at late time and you extrapolate backward in time to the near horizon region, it's a very high energy particle because of the exponential blue shift I mentioned earlier. So basically, you're looking at a very small region, the near horizon region. You're carrying out a high energy experiment. It's a little bit like Wheeler's delayed choice experiment. You're only looking at the wave packet at a much later time when it's of a large size. So it looks like it's a low energy experiment, but by nature, it's actually you're actually looking at a tiny region, a transplanckian region in the low energy vacuum. So you need UV physics to tell you what you are going to see. So I think many experts know that this nice slice argument does not really tell you that you don't need UV physics. It's not a guaranteed statement. So if you ask if Hawking's calculation is reliable, really independent of UV physics, actually that's not true because you can find Lorentz invariant quantities that goes transplanckian after the scrambling time. And more precisely, you can look at the center of mass energy in the near horizon region for a particle in the collapsing matter and an outgoing Hawking quantum. So you look at the ingoing particle, it has an ingoing momentum PV, and an outgoing Hawking particle, it has an outgoing momentum PU. And the center of mass energy is the product of the two in the near horizon region where it's almost flat for a large black hole. And the matter has a momentum that's at least 1 over A, because if its momentum is much lower than 1 over A, it has a very low probability of falling into the black hole. Its wavelength would be too long. And then the outgoing Hawking particle has a blue shifted momentum, as we mentioned earlier. So if the frequency for distant observer for a typical Hawking particle is of order 1 over A, then you see that the center of mass energy is actually of order 1 over Planck length squared after the scrambling time. The scrambling time is this expression, 2A times log A over Planck length squared. So UV physics is relevant. However, there is also another argument that people use to say, even though in principle there are UV events, at least transplanckian Lorentz invariant quantities relevant to the Hawking process, but there is still another argument for the robustness of Hawking radiation. This argument goes as this. You have Hawking particles detected at large distances, and it's blue shifted when you trace it backward in time to the near horizon region. But you don't trace it back so much that it's very close to the horizon to a very large energy. You only trace it back to a certain point where it's still a bit far away from the horizon, so that R minus A is much larger than the Planck length, but much smaller than the Schwarzschild radius. As long as R minus A is much smaller than Schwarzschild radius, the calculation of Bogoliubov transformation would work. You would predict Hawking particles if this neighborhood, not too close to the horizon, is in the vacuum state. So as long as these wave packets are not too close to the horizon, they are still not too the energy is still not too high. The energy can be still lower than the Planck energy, and so low energy effective theory would still be valid, and then Hawking's calculation would be valid, and you would predict the same Hawking radiation. So, according to this argument, it seems to be unlikely for any UV theory to change Hawking radiation. So, although if you trace it back all the way to the point closest to the horizon, you get a Transplanckian center of mass energy. But if you don't trace it back so much, you only trace it back to a point where the energy of the Hawking particle is still well below Planck mass, then you can use low energy effective theory for the prediction. So Poczynski, in an interview, said that Hawking's problem was like this. Hawking found a situation that seems to violate laws of quantum mechanics because information is not preserved. So quantum mechanics has to be modified, and Hawking is challenged us to find his mistake. And nobody found his mistake. And actually, there have been countless papers on how Hawking radiation is robust and insensitive to UV modifications of the low energy effective theory. So for us, we'd like to take a hint from quantum gravity to see how UV physics may be modified, and maybe there is a loophole to the argument we just mentioned. In string theory, one of the candidates of quantum gravity, we know that space-time geometry is actually not a unique, well-defined notion. It's actually probe-dependent. If you look at the same background geometry, for fundamental strings and D strings, they would see different geometry. If one of the two sees a metric, a space-time metric g mu nu, the other would see g mu nu times exponential dilatant to some coefficient. And it could happen that one of the two is singular, the other is regular. So in string theory, it's not always that every probe sees the same background geometry. And also in quantum field theory, we know that couplings should run. If you use probes of high energies, you could see a coupling of a different value. And so if you treat Newton constant in the same way, you would say Newton constant is running. It depends on the energy scale of the probe. So if you have a metric like the Schwarzschild metric with such a factor, you would say, okay, the Newton constant actually would depend on the probe. And when you look at Hawking particles at the later time, you extrapolate backward in time to a near horizon region. It has a higher energy and it probes a different value of Newton constant. And then the geometry is maybe not the same as you would expect in the low energy limit. So the argument above actually relies on the assumption that geometry is the same for everyone, for all probes, for all particles, you have exactly the same geometry, but this may not be the case. Furthermore, in string theories, we know that UV interactions are exponentially suppressed. Generically, for any interaction mediated by strings, including gravity, if you consider scatterings of strings at very high energies, there is an exponential suppression to the interaction. Correspondingly, in string field theories, interaction term is typically of this form. So you would have, say, a 3-point interaction term like this, phi 1, phi 2, phi 3, but we added a tilde on top to denote this expression. You have the field phi, but just with the exponential L squared Laplacian factor. So this exponential factor gives you a exponential suppression to the high energy modes in the field. So in string field theory, we typically see this kind of interactions. So you always expect an exponentially suppressed UV interaction. And therefore, you you actually would expect that Newton constant or other interaction constants to be actually depending on the energy of the probe, and then the geometry, space-time geometry, would also depend on the energy of the probe. In string theory, people have also proposed a notion called generalized uncertainty principle. So they studied string theory from different perspectives, and they came up with the same conclusion that for a string, since if you put a lot of momentum into the string or a lot of energy into the string may become longer. So you have a new uncertainty in space due to the size of the string. So then people proposed that we should modify the standard uncertainty relation of Heisenberg, delta x, delta p larger than 1, by adding another term, L squared delta p squared. So actually in these works, what they really show is that in the high energy limit, the size of the string is proportional to the uncertainty in momentum, but they just put this together with the standard uncertainty relation to make it look like this. So what we need is actually just that in the very high energy limit, when you have a large uncertainty in momentum, you have also a large uncertainty in space. And Yonea-san also proposed the space-time uncertainty relation. He wrote relations like this: delta x, delta t, larger than the string length squared. In this talk, I'm not going to distinguish string length and the Planck length for simplicity. So this relation actually is not too different from the previous one. For example, if you say you accept Yonea-san's relation like this one, then you would say, suppose I want to consider an event with a tiny value of delta t, then the usual uncertainty relation would tell you it comes with a large delta E, delta energy. And if that delta energy is associated with a large delta P, you would also expect large delta X as you would from this relation. So both relations, they show the same UVIR connection. When you take a large energy limit, you also have reach a large spatial or temporal extension. And this is the UVIR connection. When you have large energy or large momentum, you would have a large extension of string spacetime and therefore large uncertainty. So this is, we think, an important property of string theory that arises because of the string nature of string theory. And also this UVIR connection gives us a non-local effect. And this non-local effect can be large in the high energy limit. And therefore, the low energy effective theory may fail. Furthermore, even though it has a large non-local effect, I mean, delta x can be arbitrarily large if delta t or delta p is arbitrarily large. But this is not experimentally excluded because we never reach experiment with a Transplanckian energy scale. So we wouldn't know that a Transplanckian event would lead to a large uncertainty in position. And finally, as we mentioned, the fact that you have a large uncertainty in space, you expect the background space to be smeared over around the string extension, and therefore when you use a very high energy string to probe the space-time geometry, you expect the background to be a little bit smeared over, and the geometry may be dependent on the energy and momentum of the probe. So to show the idea, we draw this picture. So we have a vertical axis, the time, horizontal axis of space. This is a picture of the universe. And then we have stars and galaxies as straight lines in the universe. and then we may have a black hole here. So the black hole in the universe is a tiny dot, so its trajectory is like this, a thin line. If you enlarge a small portion of it, maybe it shows the matter before collapse, and then after collapse, it's a small black hole. So we are familiar with the concept that if you have a long wavelength mode, if you have a long wavelength fluctuation passing through the universe, if the wavelength is comparable to the size of the universe, you would use the FRW metric to describe the universe, right? You would ignore the galaxies and black holes in the universe. You would smear over the stars and galaxies and use a smooth distribution of matter to describe the background. So what's new here is that we are saying when you consider very high frequency modes, very short wavelength modes, you still have to smear over the background because you can only carry that mode with a very long string. And so when the string is as long as the universe, you would also ignore the locations of the galaxies and black holes, and then you smear everything over. You use a smooth metric for the background. So as an example, if you consider a solar mass black hole, the Schwarzschild radius is around 3 kilometers. And then you can ask, according to the UV-IR relation we had in the previous page, I mean, according to this relation, if we trace backward a Hawking particle for a solar mass black hole, you can calculate the uncertainty of that wave packet when it's traced backward to the horizon. And then you see that around 8 milliseconds after the time when the collapsing matter collapses, the uncertainty in space for this solar mass black hole is already 10 to the 53 times the size of the universe. So at that time, you wouldn't expect Hawking radiation, right? Because Hawking radiation relies on the Schwarzschild background. But at this point, you are smearing the space over such a large region, you wouldn't even see this individual black hole. So we expect that such a UV-IR relation to turn off Hawking radiation, or at least to suppress Hawking radiation after this time, which is the scrambling time, the order of magnitude of the scrambling time. Here I'm writing twice the scrambling time I defined earlier. So we have actually carried out such a calculation in more detail for concrete toy models. So we used the generalized uncertainty principle we mentioned earlier that people proposed from string theory, motivated by string theory. This gives us a minimum length, but more importantly, it tells us that at large energies, delta x is proportional to delta p. So the standard way to realize this uncertainty relation is to modify the standard, the canonical commutation relation between x and p. So you can define, for example, you can say x is I times 1 plus L squared P squared times partial P, derivative of P. And then you can plug that into your original wave equation, and you can solve the wave equation in the Schwarzschild background and then ask what happens to a Hawking particle, and then you can calculate Hawking radiation. So what we do is exactly this. We take this equation to modified wave equation in the Schwarzschild background, and we expect Hawking radiation to be modified. However, there had been many works that have done this before, and they all reported robustness of Hawking radiation. So there is a list of papers over here. They actually have already tried to do this. And so we are not really inventing a new model to realize our idea. We are actually taking a model that people have already used to study Hawking radiation for quite some time, but they all reported minor modification. However, what we did was slightly different. We considered the time dependence of Hawking radiation. So in our calculation, we looked at a particular Hawking particle detected at a certain time u0 with a central frequency omega 0. So this is the horizontal axis is the time, retarded time for distant observer. And here is a wave packet for a Hawking particle detected around u0 and has a frequency centered around omega 0. And its wave function is denoted psi omega 0 u0. So if I integrate over this wave function squared over time from minus infinity to infinity, I should get 1. And then I would get back to the standard result of a Planck distribution. But when we carry out this calculation, we found that the integral is not from minus infinity to infinity, but from minus infinity to a finite value to the scrambling time, 4a log a over Planck length. So in other works, they didn't consider the time dependence of the Hawking radiation. They were only checking for the Hawking temperature according to the Planck distribution factor. And indeed, this factor is the same as the standard Hawking radiation. So we do have the standard Hawking temperature. What's new is that when we look at the time dependence, the Hawking radiation is actually turned off because of the limit. So when the wave function is happening at the late time, after the scrambling time, this integral, which goes from minus infinity up to this point, gives you 0. So after the scrambling time, you no longer get Hawking particles. The probability or the number operator expectation value for Hawking particles after the scrambling time goes to 0. And so the interpretation is that at late times, after the scrambling time, the wave packet of the Hawking particle, when you trace it backward in time, it has a very large uncertainty in momentum, which is actually the reason why you have Hawking radiation. Hawking radiation arises because a positive frequency particle at distance is traced back to a superposition of positive and negative frequency modes. And that's why you can have a different definition of the vacuum. And so a large uncertainty in frequency is necessary for Hawking radiation. But precisely because of this large uncertainty in frequency, GUP tells you that you have a large uncertainty in space-time. And when the uncertainty in space-time is of a scale much larger than the Schwarzschild radius, your Schwarzschild geometry would look more like a Minkowski space to such high energy particles, and therefore such high energy modes no longer contribute to Hawking radiation. So there are other examples. We considered other toy models. According to string field theory, we were saying earlier that in string field theory, interactions typically arise in this way, where the fields are dressed by this exponentially suppressing factor for high energy modes. We started with this, and then we calculate the two-point function, and then we show that there is this uncertainty relation that resembles Jonasson's uncertainty relation, but this one is explicitly Lorentz covariant because U and V are light cone coordinates. And then we argue that similar to the previous example, when we have this kind of uncertainty relation, we would expect Hawking radiation to be suppressed. So actually, we are now writing a paper in which we show this more explicitly, again, by solving the wave equation in Schwarzschild background when we implement this uncertainty relation in the form that it appears in string field theory. Another natural example is non-commutative geometry. When you have non-commutative geometry, you can easily realize this kind of uncertainty, space-time uncertainty relation of Ionea. So we are also trying to do that, and the paper is going to appear soon, I believe. So again, here we see that Hawking radiation is highly suppressed, although it's not completely turned off after the scrambling time. But after the scrambling time, Hawking radiation, although it's still at the same Hawking temperature, but the amplitude decays over time as 1 over u, so inversely proportional to time. And then it leads to a lifetime of a black hole that is comparable to the Poincare recurrence time. So on the other hand, at order magnitude of the Poincare recurrence time, anything can happen, right? A typical system is going to explore every possible state in the phase space. And so it means that typically there would be classical or quantum instabilities that leads to decay or tunneling that leads to the evaporation of black hole, not through Hawking radiation, but through other classical or quantum instabilities. So the lesson we want to say is that geometry in our picture it's scale dependent because of such UV-IR relation. When you use a high energy probe to probe the space-time would look smoother than it was at lower energies. And therefore, it's possible that there is actually no horizon because the further you are approaching the horizon, there is a larger blue shift factor that goes to infinity. And but on the other hand, it sees a smoother geometry. So let's come back to the argument we mentioned earlier. People used to argue the robustness of Hawking radiation. So it was saying that we can trace back the Hawking particles to a point where it's not so close to the horizon so that it's not transplanckian, but cisplanckian, so that we can still use low energy effective theory to do reliable prediction. But this picture still assumes classical geometry for probes of all energies, right? The probe, the Hawking particle is originated from inside the shell, from the Minkowski vacuum. And if it's going to come out at a late time after the scrambling time, it must have a very large energy. And for these modes, they have a very large uncertainty in space-time. And therefore, for them, they are not going to see the standard Schwarzschild geometry. And therefore, they are not going to give you the standard Hawking radiation. And therefore, the fact that the space-time geometry is not unique to all probes of all energies actually invalidates this argument. Okay, so a few comments. There has been a lot of developments in this entanglement island proposal. So they have a formula that tells you how the entropy of a black hole follows the Page curve. It clearly involves some non-local physics because when you say you have an island inside the black hole that is identified with a region of Hawking particles outside the black hole, you are talking about some non-locality. So there is large non-locality involved, like what we had as in terms of the uncertainty relation in space-time. On the other hand, we should note that their proposal doesn't really tell us how the information is delivered from the inside of the black hole to the radiation. It actually also doesn't tell us that Hawking radiation would indeed persist as much as page time. It only assumed a radiation and could be another type of radiation. For example, it could be that Hawking radiation stops around the scrambling time, and then after a long time, maybe around Poincaré's recurrence time, there is some other classical decay or quantum tunneling that leads to a radiation, and then the black hole loses mass. They would still be able to use their formula to predict something like a page curve. So page curve applies to any typical quantum system. So as long as you are delivering qubits, you're taking qubits away from a quantum system, it would follow the page curve. It doesn't really rely on the details of the radiation. So what they showed is that indeed there is a deep connection between geometry, between gravity, space-time geometry, and entanglement entropy, but doesn't really necessarily tell you that Hawking radiation would persist. And therefore, it's compatible with our picture. And also, people now are checking information loss paradox in the context of ADS-CFT duality. So it's important for us to also consider this case, but we haven't yet. So this is our next step. What happens to a large ADS black hole? For a small ADS black hole, it's probably not too different from a black hole in the Minkowski space. But for a large ADS black hole, we have to calculate Hawking radiation for these UV modified theories over again and see what would be the difference and whether it's compatible with ADS-CFT duality. And obviously, there are applications of similar ideas. The toy models we use can be also applied to inflation. And then we would say something about Transplanckian censorship conjecture. So there are already publications about that. And also, since we are saying black holes do not really radiate after the scrambling time, actually, we are saying that black holes almost do not radiate because the radiation before scrambling time only takes away a negligible portion of the mass of the black hole. So black holes are essentially classical according to this new scenario. And therefore, there could be a lot more primordial black holes created shortly after Big Bang that persists until today. Although people usually assume that they would radiate away through Hawking radiation, but now in this new scenario, they would survive as dark matter candidates. So there are interesting implications. And so finally, let me conclude. So low energy effective theory breaks down at scrambling time for Hawking radiation. And what we show is that when we have space-time uncertainty, we can have a new scenario for black hole radiation that is different from what people usually consider. And this new scenario, it is the space-time uncertainty that turns off or suppresses Hawking radiation around the scrambling time. The space-time uncertainty tells you that at late time, Hawking particles are blue shift to a high frequency mode, which smears over the space-time geometry. And therefore, as a result, black holes are essentially classical because it hardly radiates only a little bit. So in this picture, actually, we have the most, in some sense, the most conservative picture about black hole radiation. Black hole radiation is a quantum effect, and typically for macroscopic objects, quantum effects can be ignored. And we are just saying that. Hawking temperature is not modified, so if you use the standard arguments about Bekenstein-Hawking entropy from Hawking temperature, you would get the same Bekenstein-Hawking entropy. And so black hole thermodynamics is not much modified. You can say most of the same things as before. Because basically we are not changing Hawking temperature, we are only changing the time dependence of the Hawking radiation. So it's a little bit like having uh, a black body radiation, and black body radiation is typically realized by having a box and you drill a small hole in the box. And then when you look at the radiation coming out from the little hole, it has the black body radiation spectrum. But if the size of the hole is time dependent, then you would have the same temperature from the black body radiation, but the time dependent amplitude. So what we're saying is a time dependent amplitude, but the same temperature. And also, the space-time uncertainty blurs the horizon. The horizon is no longer a well-defined location because the geometry is not well-defined for, it's not independent of the probe. So the geometry is probe-dependent, and therefore horizon could be also probe-dependent. And then other channels of information radiation may happen, like in the first ball picture, for example. They found that there are classical instabilities that gives a new type of radiation. They still call it Hawking radiation, but it's actually a total different thing. So if we define Hawking radiation according to the original work, it is just reinterpreting the Minkowski vacuum inside the collapsing matter. So by definition, it doesn't carry information of the matter. But there could be other ways of information. And every other way of information, like from classical instability or quantum tunneling, you would not have information paradox. The information, how information comes out through other channels are typically clear. So in this way, we have a new scenario as a new resolution to the information paradox. So that's the end of my talk. Thank you.
Okay, thank you, Pei-Ming. Very nice talk. Uh, any questions from the audience? Maybe let me start with one. So I have a I'm a bit confused about the integration of the amplitudes of the wave functions from minus infinity to this scrambling time. So my understanding from your talk is that this integration, or in particular integrants inside this integral, goes to almost zero after scrambling time due to this UV modifications. So I think in principle you can really integrate from minus infinity to infinity, right? And you get the same
This is a
results.
result of our calculation. So by modifying the wave equation in Schwarzschild background using this relation, we follow the same calculation as before. And it turns out that the only change is to change the upper bound of
Oh,
integration from infinity to this number. So this commutation relation introduces this length scale L, and that shows up in here.
so it is really like this integrand doesn't exist after the scrambling time mathematically. Can it?
Yeah, yeah. Of course, in the derivation, we have used some approximation. For example, we have to say that the central frequency omega zero is a good estimate. I mean, the width of the frequency spectrum is much smaller than omega zero, things like that. So
Mhm.
using those assumptions, you typically make about the wave packet. You can have this approximation, and then the integral goes like this.
I see. And why scrambling time? Do you have like any physical interpretation why
Yeah,
specifically this happens after
yeah. The
scrambling time?
reason is that the characteristic scale is Planck length, and the scrambling time is the time at which you trace the particle backward to the near horizon region, and its center of mass energy becomes transplanckian. Earlier we had a um, wait, where? Yeah, here. So we have a Lorentz invariant quantity, which is the center of mass energy between collapsing matter and outgoing Hawking particle. So when this invariant quantity goes transplanckian, your UV physics may take place, right?
Yep,
So scrambling time is the time at which this quantity goes transplanckian.
I see.
Yeah. So the thing is that people have also considered a lot of different UV physics. They all reported minor modification to Hawking radiation because even if some UV physics becomes important around scrambling time, as long as you can still use this argument, it's not going to change Hawking radiation much. For example, people have considered modified dispersion relation such that when you chase a particle backward in time, it would never get into deep inside the matter, but it would bounce back to large distance. So even in those very strange models, they predict the same Hawking radiation because of this argument. So this argument is robust as long as you have a well-defined space-time independent of the probe. And then even after scrambling time, you don't have much modification. So here we always need scrambling time to expect anything to happen. And furthermore, because of this argument, in order for something to happen, you have to modify the classical geometry somehow.
I see. Thank you. Any other questions from the audience?
I have one question. So there are several situations in which something like Hawking radiation is observed, like moving mirror or supersonic Hawking radiation. And do you expect similar sort of modification required to such systems?
Right. So, for example, we considered Enroux effect. In Enroux effect,
Uh-huh.
we don't see any modification even if we modify the UV physics, because in Enroux effect, there is nothing that actually, I mean, everything can be Lorentz boosted, right? So there's no real notion of transplanckian energy because it's talking about Minkowski space. But for black hole, and so actually I should have emphasized that I'm talking about dynamical black hole, not permanent black hole.
I
I
see.
don't have translation symmetry in time. I do have some initial time and late time. So I have a black hole in the middle. I have a notion of Lorentz invariant quantity that goes transplanckian. So I think when we do have a Lorentz invariant transplanckian quantity, we would expect some large modification to the usual story. But when we don't have it, we would not.
Okay. Thanks.
Thank you.
Any other questions? Okay, I didn't see any other questions. So if no, let's thanks Pei-Ming again, and let me stop the recording and end this